Okay, welcome to the presentation of the Call for Technologies, Mpai AI as a Service, which is the Mpai AI-MAS version 1.0. This is an online presentation on the 30th of March, 2026 at 1500 hours UTC. The evolution of computing, raw computing services, CPU cycles, memory allocation, network primitives, file systems, these represent the foundational substrate of computation. Tight coupling between applications and infrastructure, limited portability, modularity, and scalability. These are some of the restrictions of this paradigm. Hardware complexity, abstracted by operating systems, middleware, and cloud services. But AI introduces new demands. The demand for heterogeneous compute, CPU, GPU, TPU, different types of hardware, distributed execution, dynamic model composition, real-time communication and event pipelines, cross-platform interoperability, trust and security for ML components. MPAI provides standards for AI. MPAI, moving picture, audio, and data coding by artificial intelligence, an international, unaffiliated, non-profit association based in Geneva. The MPAI mission is the promotion of the efficient use of data by developing technical specifications for the coding of any type of data, especially using artificial intelligence, technologies that facilitate integration of data coding components in IICT systems, and by bridging the gap between technical specifications and their practical use through the development of intellectual property rights guidelines, the IPR guidelines. MPAI operation is based on an international collaboration of interested parties, supporting the MPAI mission and the means to accomplish it. There is a need for an AI application execution environment. The AI Framework Standard, MPAI AIF, a layer above raw computing services, providing standard structure, standard interfaces, and standardized behavior. This framework, as we can see in this diagram, shows the user input to the AI workflow. An AI workflow comprising a collection of AI modules. These modules are retrieved from the AIM storage, collaborating, working together, output from modules to input of other modules, eventually giving rise to the output of the overall AI workflow. This is managed by the controller layer, and the controller working in conjunction with the communication, global storage, access, and of course, the MPAI store. The controller is for managed orchestration. The controller handles scheduling, resource management, communications, and interactions with the MPAI store. The controller abstracts raw execution by managing communication between AI components, activating, suspending, and managing the workflows, running workflows across multiple computing platforms, and also allowing the hot plugging of modules. No manual composition of computational services is required. Orchestration is systematic and programmable. Modular compute units. Each AI module, or AIM, encapsulates its algorithms, its models, its processing functions behind standardized ports and event interfaces. No raw compute primitives are required. The key AIM characteristics include standardized input and output ports, independent execution, local or heterogeneous hardware, hot plug capability, AIMs can include other nested AIMs, composite AIMs. Computation involves interoperable modular building blocks, allowing reuse and composition without rewriting infrastructure. All of this behind a standard API. The Mpai AIF specifies a rich set of API enabling the controller to download modules and workflows from the Mpai store, allowing the user agent to call the controller, allowing the AIMs to control the controller. The Mpai AIF API composes primitives to allow the store to be accessed by the controller, the get and pass archive, allowing the controller also to be called by the user agent. General features, general functions, inquiry about the state of AIWs and AIMs, the start, pause, resume, and stop messages to other AIWs, management of shared and AIM storage for AIWs, communication management, resource allocation management. It also provides APIs for the controller to be called by AIMs. General features, resource allocation, registering and deregistering modules of the controller. Of course, the start, stop, pause, resume messages to other AIMs, registering connections between AIMs, using ports, operations on messages, functions specific to machine learning, and the controller API can be called by another controller. AIF is a new layer above the raw compute. The move from raw computing services to the Mpai AIF architecture parallels the evolution of machine code towards high-level languages, or physical networking towards software-defined networks, or ML pipelines to platform-managed AI ecosystems. AIF provides the missing abstraction layer, enabling interoperability, modularity, and distributed execution. AIF transforms computation into standardized, orchestrated AI workflows, making raw compute services simply an implementation detail. The current requirement is that it be local and not remote. Mpai envisages the MAS service where a remote client application, hereafter referred to as the RCA, can select an AI workflow amongst those available in the Mpai store. A service controller instance, hereby referred to as the SCI, downloads and executes the AI workflow. The RCA retrieves outputs resulting from the execution of the workflow. To leverage the availability of AIMs and AIWs from various sources, MAAS requires ubiquitous access to the Mpai store to support envisaged application scenarios. It requires to be guaranteed the highest level of authorization when accessing AI workflows and their constituent components. And it must exercise the highest level of authenticity control on AI workflows and their constituent packaged components. This calls for technologies, Mpai AI as a service, otherwise known as MAS. Mpai AIF design is driven by the need to locally execute AI workflows. MAS moves the current user-centric view of Mpai AI to the centralized view of the MAS service provider. In MAS, users can instantiate controllers, download and execute AIWs, provide their own data, and obtain the results of their processing. The MAS call intends to extend current standards to enable remote access to remote AIF facilities. Here we have the diagram of the reference architecture of Mpai AI as a service. The three boxes at the bottom in green represent the elements, the concrete elements, the client application, which is remote, the controller, which is central, and the MPI store, which would be accessible from the controller. The blue boxes above show the APIs that are required to allow the standardized access between these fundamental elements. Client application makes functional requests to the API client, which wraps the API requests, HTTPS of course, that are sent to the API server. The API server performs the operations required, instantiating the controller and communicating with the controller. The controller receives the request from the API server for the startup of a workflow. It will communicate with the MPI store to retrieve the elements required for the startup of the workflow, and then it will launch the modules and also communicate with those modules in response to input messages received from the client application and requests from the client application requiring output messages delivered as a result of the execution of the workflow. Here we have a 13-point workflow of Mpai as a service. Point 1, the remote client application issues a service controller instance creation request. It does so through the API client, and this is received by the API server. The API server returns the ID of the newly created service controller instance. It sends it back to the RCA. Now, the RCA, using this service controller ID, issues an AIW instantiation request through the API client to the API server, and finally received by the SCI. The SCI issues a request for an AIW to the MPI store. In the simple case, the MPI store simply returns the requested elements to the SCI. In a more complex scenario, an MPI store would issue subsequent requests for further elements to remote repositories. These remote repositories would return the requested elements to the MPI store, which would then be returned to the SCI. The SCI returns the AIW ID back to the remote client application so that the client knows the ID of the workflow it has started. The API server returns the AIW ID back to the RCA. The remote client application can now issue messages to input data to this started workflow. It can also issue messages to receive outputs from the ports of the started workflow. The SCI naturally will return the data, having retrieved the data from the appropriate module of the workflow. The API server will return the messages to the RCA, and the RCA eventually, when it has no longer any need for the module and workflow, will issue a termination request for the workflow, and then eventually a termination request for the service controller. Here we have this shown in a different way. The client application on the outside to the MPI store on the inside, a more layered approach. As we go around clockwise, the client application requires to create a controller. It issues a request through its API client to the API server, which instantiates a controller. The client will then send a start workflow through its API client to the API server and to the instantiated controller. The controller will fetch the components from the MPI store and start the workflow, returning the ID. The client application can then send input messages to the controller so that the data will be delivered to the input ports of the modules of the workflow. The client can then issue request messages for output from the output ports of the workflow through the API client to the API server to the controller. Finally, when the client no longer has any need for its AI workflows, it can issue a stop workflow through the client to the server to the controller, and at the end, can request deletion of the controller instance. Here we have an overview of technologies that are envisaged for the MPAI store. The MPAI store may comprise elements such as the update framework, which provide rigorous control over versioning and authenticity of components, may comprise elements of a distributed file system, such as the Hadoop distributed file systems, HDFS, ABFS, quite a variety of different implementations. It could be a cloud object store API, such as the S3 object store. It could be an open source object store, such as the Swift API, or it could be quite simply an HTTPS file API. Underneath, we see the update framework, which provides the technology that is accessible through the TUF API. We have a Hadoop-compatible distributed file system, which would respond to the APIs for the distributed file system. Naturally, an Amazon S3 compatible, or even the commercial instantiation could handle an object store, the OpenStack Swift object store, and finally an Apache web server. These are all examples of types of these APIs of which the MPI store could be composed. Naturally, each of these would be reposing on a file and object storage repositories containing the components and the workflow descriptions and the module descriptions that would be returned in response to the request to the MPI store. This mass call requests an architecture for the management of the MPI store and the subordinate distributed repositories. It requests protocols that are considered suitable for supporting the specific requirements. Alternatively, a single interface enabling service controller instances to access a plurality of repositories, each supporting different protocols. Solutions proposed may be original, or they may rely on existing technologies, or any integration thereof. If needed, proposals for revision of the MPAI AIF basic API may be submitted to accommodate requirements of the proposed technologies. To submit a proposal, read the call for technologies. Then, accept the framework license. You may then send inquiries to the Secretariat at mpai.community. If you have any questions, you should respond using the template for responses. Your response should be submitted by the 13th of April, 2026, by 1500 UTC. You must also join MPAI to participate in the MPAI mass development. The proposal evaluation will be as follows. The completeness of the description. A detailed description is highly recommended. The understandability of the description. Again, a detailed description is highly recommended to ensure that it is fully understandable. The implementation complexity and technologies that are potentially usable to implement the proposal will be very important. The reliance on established technologies. When assessments are similar, preference will be given to proven technologies. The availability of reference software is very important. When assessments are similar, preference will be given to those technologies for which a running reference software is available. The existence of essential patents. A proposal that is not encumbered by IP may be selected against a functionally equivalent unencumbered proposal. Here we see the range of AI modules and subjects which have already been addressed by the MPAI community. The AI framework, AI for health, audio enhancement, automotive, finance, gaming, governance, human-machine communication, the metaverse, multimodal conversation, neural network watermarking, NNW traceability, NNW technologies, objects and scenes, portable avatars, profiles, qualifiers, upsampling of video filters. The range is vast, and all of these subjects would be available through the MAAS remote system. So, join MPAI, share the fun, and help us to build the future. The MAS documentation is available at the MPAI community standards MPAI-MAS. Submit innovation and inspire transformation. Join MPAI at the MPAI community, how to join. Thank you very much. Are there any questions?